Electronics
This
and
conference
Communication
will now be
Engineering
recorded.
from NSS College of Engineering, Palakkad, under University of Calicut in 1998, and MTech in Optoelectronics and Laser Technology from International School of Photonics, Cochin University of Science and Technology in 2001. After working at Research Center Imarat, DRDO, Hyderabad on integrated optics for 2 years, he left for Republic of Korea, where he did his PhD and postdoctoral research at Gwangju Institute of Science and Technology, focusing on 3 to 5 material-based microring resonator switches, electro-absorption modulators, optical interconnects, and multi-junction solar cells. He joined Department of Avionics, Indian Institute of Space Science and Technology, Trivandrum, and is presently working as an associate professor, where his research activities focuses on semiconductor optoelectronic devices, multi-junction solar cells, plasmonics, and microring resonator-based switches and modulators. He is also involved in the facilitation of clean room and semiconductor fabrication tools upcoming at IISc Trivandrum. Now, on behalf of Government Model Engineering College Kochi, let me invite Dr. Sooraj Ravindran to deliver his lecture on optical modulators and switches. Over to you, sir. Sir, is there any problem? Hello? Participants, please wait for a while.
is on എന്നുള്ളത് ഇപ്പോഴും ഇപ്പൊ കേൾക്കാം.
Suraj sir, now it's audible.
ശരി, ഓക്കെ, താങ്ക് യു.
Okay. Over to you, sir. You can continue your presentation. Hello, sir. It is not audible here.
ഈ ലൗഡ് സ്പീക്കറിന്റെ സിമ്പിൾ ഓൺ 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 തന്നെയാ, കേൾക്കുന്നുണ്ടോ?
Suraj sir,
ഓക്കെ, ശരി.
it is now audible.
So I hope I am audible now.
Yes, sir.
Is it? Okay, thank you. So I'm extremely sorry for this technical difficulty. So, okay, so today I would like to share my knowledge on optical modulators and switches. Some of the work has been carried out at Korea, and some of the work has been carried out while I have started my work at Indian Institute of Space Science and Technology. Okay. So our topic of discussion would be optical modulators and switches. So in fact, we are going to have two sessions. So one is from 10 to 11:30 and the other one is from 11:45 to 1:15. And I think the organizers have arranged probably optical switches as the first one and optical modulators as the second one. But it turns out that there is not much difference between these two devices. And accordingly, I would like to take both the sessions as one, but nevertheless, we'll be having a short break from 11:30 to 11:45. So in case if I am unknowingly exceeding the time limit, please remind me at 11:30. Okay,
Sure,
so
sir.
for today's talk, for today's discussion on optical switches and modulators, so these are the topics what I would like to we would like to have a conversation on. So I would discuss on optical modulation. I will explain what is mean by optical modulation and what is mean by optical switching, and I will also introduce the need for optical modulation and optical switching. I will then explain what are the various mechanisms by which will the different device switching and modulation. We'll also see what are the configurations by which we can perform optical switching and modulation. Now, there are materials by which you can construct an digital switch, an optical switch, and you can construct an optical modulator. Now, of the various semiconductors, they have specialty. So, my talk, in fact, our talk today would be focusing on optical switches and modulators that are based materials. For that are based on materials. I would also like to give you some brief introduction about some of the fundamental properties. Now, modulate 3-5 semiconductors. They are switches and more used in systems.
Excuse me, sir.
Optical
Hello.
communications generally don't really worry
Excuse me, sir.
important. But if you want to make the size of the device very small, thereby you want to create what is called as an integrated circuits, then there are special configurations of optics and a modulator which is for tell me.
Sir, your sound is
Hello.
breaking. Hello, sir. Can you hear me?
Hello.
Hello, sir.
Now?
Your sound is breaking. Hello.
The voice is still gone?
No, sir. Your voice is breaking.
I can hear you. I can hear you.
Yes, sir. We can hear you, but in between your voice is breaking. Is there any network issue there?
Well, now
Hello, sir.
audible.
Yeah, sir. You're audible, but
Hello.
the hello, sir. Your voice is
Yeah, am I
breaking.
audible now?
Yes,
Yeah, am
I think there is a network issue.
now?
Yeah, in between we can hear you.
Yeah, I don't know what is wrong with my internet connection.
I think there is the problem with the internet connection. Dear participants, sorry for the inconvenience. There is some network issue with the presenter. Please kindly wait for a while.
So am I audible now?
Yes, sir, you're audible.
Now?
Hello, sir, it's audible now.
Yeah, all right. So I don't know where I am. Okay. Okay, thank you. Yeah. So I'll briefly introduce about the need for modulation and optical switching. I'll explain about the various mechanisms that can enable optical modulation and switching and the various configurations and of the various materials by which you can construct an optical switch and a modulator. 3-5 semiconductor based optical switches and modulators have certain advantages. I'll briefly introduce 3-5 semiconductor based optical switches and modulators, and I'll also introduce about a particular configuration which would be highly beneficial in realizing an optical integrated circuit where you can really miniaturize the size of optical devices, thereby you can realize an integrated circuit very similar to an electronic integrated circuit. So the device called as an optical switch and an optical modulator is usually used in an optical communication system. So here is a block diagram of an optical communication system. So the system is very similar to a conventional electrical communication system where you have a transmitter. So you have a transmitter over here, you have a receiver, and you have a communication channel which connects the optical transmitter, or in fact the transmitter and the receiver. So the job of a communication system is to send signals, to send information signals from the transmitter to the receiver. And the job of the communication channel is to carry that information signal from the transmitter to the receiver. So if you look in detail about the block diagram of an optical transmitter, you are going to have a source. You are going to have a source which gives off electromagnetic signals. So in fact, this source, the source what you see here, this optical source what you see here would be usually a laser diode, or an LED or a light emitting diode, which is going to give out photons. So the signal from the optical source is going to be going to be launched inside an external device, which is called as an optical modulator. So this is an optical modulator. This is an external device which is usually placed outside the optical source, and we'll very soon see why you have to externally keep this. Now to this external device, you are going to give what is called as the electrical input. And in fact, this electrical input is actually the information signal what you want to send from the transmitter to the receiver. For example, your voice signal. You want to send your voice signal from one place to another, and therefore this information signal is what is called as so this will be the voice signal, and you will have to send this voice signal from the transmitter to the receiver. Now coming to the receiver side is going to have a photo detector whose job is to receive the photons and convert it into electrons and holes. It's going to convert light into electricity, and that current will be demodulated, and ultimately you will get this electrical output, which is the same as the voice signal what you had sent before. So this is the transmitter side and this is the receiver side. So between the transmitter side and the receiver side, you have a communication channel, and this channel could be either air or it could be an optical fiber. It could be an optical fiber or it could be an optical waveguide. It could be an optical waveguide. So these three, so if it's air, you call it as a free space communication, whereas if it is an optical fiber or a waveguide, you call it as a guided communication system. So whatever be the kind of communication system, whether it is guided or unguided, optical modulators and optical switches, they form an essential part of any optical communication system. So if you look, so this is another block diagram of an optical communication system. In fact, it's the same thing, but only thing is there are some more external devices that are being shown. Now imagine that you have a transmitter and a receiver. Now somewhere in between, so receiver is a user. In fact, this receiver is actually a user. So let me call this as user 1. Now imagine that there is another user, who also would like to receive some of the signals. So transmitter is sending signals, and this signal has to be sometimes will have to be sent to user 1, or sometimes will have to be sent to user 2. And therefore in that case so in between the communication channel you would actually introduce a new device which is called as an optical switch. So here you can introduce a device which is called as an optical switch. So this optical switch, what it does is, depending upon a control signal, the signals that are being sent by the transmitter would be either transmitted to user 1, or it would be sent to user 2, depending upon the control signal. So you have an external control signal which will be actually deciding the destination of your received signal. So such a device which does this function, is what is called as an optical switch. So in fact these are the so this is why you would like to have an optical switch and an optical modulator. So before we go into the details of an optical switch and an optical modulator, let us see how the signals are being represented in optical domain. So imagine that you have a voice signal. So this is a voice signal which is analog in nature. So this is an analog signal. It's an analog signal because this is a continuous signal. So it's a continuous signal in time. Now you would always like to convert this continuous signal into what is called as a discrete signal, or in other words a digitized signal. So this is a digitized signal. So this continuous signals, which have a continuous variation of amplitude with respect to time, is being converted into a digital signal which is usually represented in the forms of 0 and 1. So you convert this continuous signal into a discrete time signal which is represented in the form of zeros and ones. Now you would like to send this signal. So you have your information signal, and this information signal has to be sent. And since we are talking about the optical signals or optical communication systems, we are actually using a photon. So we are using a photon, and a photon is nothing but an electromagnetic wave. And an electromagnetic wave, in fact, an electromagnetic wave can be represented as A naught sine of omega t plus phi, where A naught is the amplitude of the signal, omega is the angular frequency of the signal, and phi is the phase of the signal. So in fact, if you carefully look at how the signals are being represented and electromagnetic signals are being represented, there are three parameters, which are the amplitude, the frequency, and the phase of a signal. So in fact, you can change any one of these parameters. So you could change either the amplitude, you could change the frequency, or you could change the phase of the signal. So if you can change the amplitude of the signal, if you can modulate, if you change the amplitude of a carrier wave, so this in fact is the high frequency signal, and this is light. So in the case of optical communication system, the carrier wave which actually carries the information signal is light. So this is photon. So this is photon which actually carries the information signal, and in fact this modulating wave, this is the information signal. So this is the information signal what you want to send from the transmitter to the receiver. So depending upon whether you change the amplitude or the frequency, you can call this kind of modulation as an amplitude modulation or a frequency modulation. So in fact, you all know this because these are all the basic concepts of any communication system. But in general, for an optical communication system, rather than going for frequency modulation, we generally go for what is called as an amplitude modulation. But there is some fundamental difference between the amplitude modulation what you see in analog systems or in the conventional electrical communication systems, and the amplitude modulation what you have in the case of optical systems. So in the case of optical systems, we generally send signals in the form of ones and zeros. So 1 and 0. So 1 represents, this represents the presence of photon. So this means you have photons. So you have photons, and 0 represents absence of photons. So this represents absence of photons. So a presence of photon indicates a digital 1. It indicates digital 1, and the absence of photon, that means if you don't have light, then you would represent it as 0. And by this combination of presence of photons and absence of photons, you can actually convert this electrical signal into optical signal, and then you can send this. So in fact, so here you have a train of digital signals, but in fact what these are, in the case of optical domain, what you have here is actually a train of optical pulses. So you have a chain of optical pulses or a train of optical pulses, and in fact these chain of optical pulses passes through an optical fiber, and ultimately it arrives at the receiver. So this is how a conventional optical communication system is going to work. And you all know the fundamentals of how you can convert the signals. You will have to always use what is called a sampling, and obviously you will have to always obey the Nyquist criterion. So since these are all common with electrical communication systems, I'm not going to go into the details of that. Now, the signals that are flowing through a communication channel could be either in the form of an optical fiber, So this is an optical fiber, or it could be in the form of a planar waveguide. Now, once the signal enters the fiber, you really don't have any control on the signals that are flowing through. You cannot do anything on that. So if you really want to control the signal, if you really want to modulate the signal, this modulation can be done before the signal enters the optical fiber. That means before this electromagnetic signal, before the photon enters the optical fiber, you'll have to do all kinds of manipulation on the photon so that you can really achieve what is called as optical modulation. So optical modulators in general, they usually have a configuration of a planar waveguide. So all optical modulators, what we are going to discuss in today's lecture, is going to have a configuration of a planar waveguide. So what is a planar waveguide? So you have a device in the form of a planar structure. So N1 and 2, so N1, this white region, what you see here is the core region, which has a higher refractive index compared to these two yellow regions. So this is a planar structure, and this planar structure usually sits on the top of, so this is actually placed on the top of what is called as a substrate. So you have what is called as a substrate, which actually carries this device. So it's on this substrate that the device, the optical modulator and the optical switch actually rests on. So the substrate is also very important. So in fact, the materials what you're going to use, so the material that comprises of N1 and N2, they have to be properly sitting on the top of the substrate. So in the context of material engineering, you describe that proper sitting as what is called as lattice matching. You call it as lattice matching. That means the lattice constant of the material, of this yellow material, the lattice constant of this white material, and the lattice constant of the substrate material, they should be all the same. So in fact, if any one of you don't know what is mean by lattice constant is, the lattice constant is actually the distance between the adjacent atoms of a semiconductor material or a semiconductor lattice. So you have in a lattice, you are having periodic arrangement of atoms. You're having atoms that are periodically arranged. So this is atom 1, atom 2, and so on. And so if you consider this line as the interface between this white material, between this yellow material and the substrate material, the substrate material will also have some atoms. So this also will have some atoms. So this spacing, the distance between the adjacent two atoms, is what is called as the lattice constant. So this lattice constant should be the same as this lattice constant. So this is an essential requirement in constructing any optoelectronic device, and which is true in the case of optical switch as well as in the case of optical modulator. So I said that the information signal is being sent in the form of 0 and 1. So 1 means, so whenever you are sending 1, it means that the light is being guided by this core region. So this white region is the core region. So this region is the core region. So this core region is going to confine the light whenever you are sending 1. And if you are sending a 0, it means that either it could mean two things. One is either the core is actually absorbing all the light. The core is absorbing all the light. So one condition is that the core absorbs all light. The second condition is that the second condition could be the light that was being guided by the core is now being guided by the cladding. That means the light has been switched to the cladding. The light is no more guided by the core. So the core is not guiding the light. The core is not guiding the light. So this is how you send the information signals in a planar waveguide in any optical communication systems. So obviously, in the case of an optical fiber, you're always going to have. So this is the cross section of an optical fiber, and you are going to have the light is being guided by using what is called as total internal reflection, which is based on Snell's law. So in fact, this planar waveguide also, though the geometry is different, optical fiber has a circular geometry where this has a different kind of geometry. This has a rectangular geometric structure, but nevertheless, the concept of light guiding is always the same, which is called as the total internal reflection. So this is the fundamental principle by which the light is photons are being guided by the planar waveguide. Now I said that all the optical modulators and switches, they usually have a planar structure, and you must be having a waveguide. So you must be having a waveguide. So whenever we talk about a waveguide should be having two things. One is it should be having a core which has a higher refractive index, and then it should be having a cladding which is having a slightly lower refractive index. So in fact, these are the various geometries that are possible for constructing an optical waveguide. Sorry, for constructing an optical switch and an optical waveguide. So in fact, this shaded region, what you see here, is the optical waveguide which has a higher refractive index. So this material has a slightly lower refractive index, and this region, they also have a slightly lower refractive index. So there are different configurations. In fact, there are different waveguide configurations which can actually support optical signals, and you would probably hear more about this when you have a talk tomorrow on optical integrated circuits. So you would probably hear more about these kind of waveguide structures in tomorrow's class. Nevertheless, these are the commonly used waveguide configurations for constructing optical switches and modulators. Okay, now so here is one of the configuration for an optical waveguide, which is actually commonly used for constructing optical switches and modulators. Now, for these kind of waveguide structures, so if you draw a waveguide, let's say you are physically drawing a waveguide, you draw the waveguide like this. But when you actually make a waveguide, so that is, so this is the microscope image of an optical waveguide. In fact, this is what is called as a ridge waveguide, RIDGE. It's called as a ridge waveguide. It's called as a ridge waveguide. So you will see that you actually expected a rectangular geometry, but what you're going to get is not exactly a rectangular geometry, but it's something close to rectangle, is close to a rectangle, but you will see that you have lots of corrugations there. So these irregularities are called as corrugations. They are called as corrugations. Now these corrugations, they actually cause what is called as scattering loss. So whenever signals are flowing, whenever photons are flowing inside this optical waveguide, rather than finding a smooth geometry, it would always find a rough geometry. And because of that, you have what is called as scattering of light. So scattering of light. When scattering happens, the light that was the photon that was initially there inside the core would now go to the cladding. That means you are actually losing information signal. So please remember, the job of a communication channel is to carry the entire signal, to carry the entire information signal and then deliver it to the receiver. But once you lose the signal, the information signal is lost. That means the receiver will not be able to properly decide whether the transmitter had sent a 1 or the transmitter had sent a 0. So if there is some kind of ambiguity in the decision making process of a receiver, that is when the receiver would actually make what is called as an error. It would actually create an error. And when the receiver makes a lot of error, that is when at the receiver side you don't get any signal. So just now we had a voice break. That's because the receiver did not properly receive the signal, and it's probably because of lots of scattering and lots of signal losses that happened from the transmitter to the receiver. So it's very important that in any optical communication systems, and in fact, whenever you are designing an optical modulator or an optical switch, and which is having a waveguide configuration, this scattering loss will have to be minimized. So this should be minimized. So this is the takeaway from this slide. So this scattering loss should be always minimized. So this should be minimized. That means you should make very good waveguides. Okay, so so now we spoke about modulation, and in fact we are going to talk about optical switches and modulators. So let me once again explain what is meant by modulation. Modulation simply means you are changing. So modulation means you change something. The change is what is called as modulation. So what do you change in the case of an optical signal? What is the most easiest parameter what you can change is the amplitude. So we have seen that amplitude means it indirectly means you are actually changing the intensity of light. So remember, so this is one of the fundamental difference between the electrical communication system and optical communication system. So in this case, you change the intensity of light. Intensity, in fact, essentially translates to the number of photons. It essentially translates to the number of photons. So it essentially translates to number of photons. Now, a photon can be created by using two sources. There are, as I said before, there are two optical sources which can create photon. One is the laser diode. The other one is the LED. In fact, the common thing among both of this is a diode. This is also a diode. Both are diodes. A diode is nothing but you have a p-n junction. So you have a p region, you have an n region, and then you apply a forward bias. You connect a battery. So the p region is going to have a large number of holes. The n region is going to have large number of electrons. So when you apply a forward bias, these holes and electrons recombine. So electrons and holes recombine. And this recombination, because it happens in the case of a direct bandgap material, so this electron and hole recombination would result in what is called as a photon. So this, you would generate what is called as a photon. Now, how do you create this electron in the hole? You create this electron in the hole by an external voltage source. You have an external battery. So this battery actually produces a current. This battery produces a current, and this current is the one which is actually generating these electrons and holes, causing them to recombine. So now if you look at the inside of a PN diode, you will see that because of the applied voltage or because of the applied current, you are actually creating large number of electrons and holes. Now these electrons and holes, they recombine. The electrons and holes recombine to create what is called as a photon. So you would note that when you apply a bias, so when I apply a bias, this would create electron and a hole. Now this electron and hole, so biasing creates electrons and holes, so therefore their numbers are increasing. Now once the electrons and holes are produced, they would recombine. Recombination means an electron from the conduction band falls to a vacancy in the valence band, and in the process the excess energy is being released as a photon. So that is what is called as a recombination. So once they recombine, so recombination means, so when they recombine, the electron and hole, they recombine, they create a photon. So they would create a photon. That means the total number of electron and hole density inside the diode decreases. So by applying bias, you are increasing the electron hole population. By recombination, you are actually decreasing the electron hole density, which means that there is a net change of electron and hole density inside a semiconductor diode. And so therefore you can always write a relationship between the increase in the electron density because of the current generation, because of the applied current, and the decrease in the electron and hole density because of the recombination, because of the production of photon. And that relationship is what is called as the rate equation for an LED and a laser diode. It's called as the rate equation. So a rate equation actually relates the electron density. So I would denote the electron density as N. So dN by dt. So I would write the resultant change in the electron density as the current, the total current that is flowing through the diode divided by the charge of the electron divided by the volume of this diode, because it's under this volume that the electron hole recombination happens or the electron hole generation happens. So because of the current that is flowing, this is the total amount of electrons that are being generated. Now from this electron, you are going to have, so some of the electron, so you are going to lose some of the electron because of, so you are going to lose some of the electron because of recombination. So there is always a recombination lifetime, the time required for the electrons and holes to recombine, the time for which an electron stays in the conduction band, after which the electron would fall to the vacancy and recombine. So that time for which the electron stays in the conduction band is what is called as the recombination or the carrier lifetime. So after that time, the electron would actually come back and it would recombine with the hole and it would produce a photon. So this term would represents the increase in the electron density, whereas this term represents the decrease in the electron density. So the net difference is what is called as the rate of change of the electron density. So this differential equation is the fundamental equation which governs the modulation in any laser diode as well as in LED. So from this equation, you will see that the electron density increases and decreases and there is a net change. Now if I assume that now the signal what you are sending, the signal with which you are actually changing the signal what you are giving to the laser diode is actually the information signal. So you are giving in the form of a current, your voice signal. Now this voice signal is going to have a DC component and an AC component. Your voice signal will always have a DC and an AC. So the current is going to have a DC and an AC component, and accordingly you will note that the electron density, the change in the electron density inside the diode is also going to have an AC component and a DC component. So if you solve this rate equation, if you solve the rate equation for an LED or a laser diode, you would see that the optical power or the light power. So here is a plot of the optical power from a light source as a function of the current. So you are applying a current to the laser diode or a LED, and it's actually creating photons. So this gives off light. So the measure of this optical power as a function of current is being actually plotted in this graph. So you can see that by simply changing the current that is given to the laser diode or an LED, you can actually change the intensity. So this light power is nothing but the intensity. Is nothing but the intensity of the light. So you apply a small current, the light intensity is very small. You apply a large current, you will have a large intensity. You'll be having a large output from the laser diode or an LED. So this graph is actually the relationship between the current as a function of optical power from an optical source. So you will see that the common factor between the light emitting diode and a laser diode is that by changing the input current, by varying the input current, you can actually change the output power of a light source. In other words, you can actually modulate the output power from an LED or a laser diode. So this process by which you change the output power of a light source by directly changing the input current is what is called as the direct modulation. So this modulation process is called as direct modulation. It's called as direct modulation. So direct modulation means you change the current, you change the drive current, and you change the output intensity of a light source. So in fact, earlier days in the optical communication systems, so engineers would always prefer to work with what is called as the direct modulation. So modulation is again the process of you have an information signal, and you encode that information signal on a high frequency signal. So the device which does this is called as an optical modulator. Now in the case of optical domain, there are different modulation mechanisms by which you can change the intensity of a light. You can change some of the property of the light. So I said long back that in the case of waveguide devices, whenever you are changing, so in the case of a waveguide, you have a core and you have a cladding. So whenever you say that you are sending one, the core will be containing the information signal. The information signal is nothing but photons. So one is nothing but photon. So I'm going to represent h nu as photon, and the cladding will be 0. That means you are going to have no photons there. Now, if you don't want your optical waveguide to send a signal, that means the core should be now 0. The core should be now containing 0. That means the core should be having no photons there, and the photons could be present. The photons could be present in the cladding. That means you are basically changing the optical confinement of a waveguide. So this is the fundamental. This is the fundamental parameter what you are changing. In some of the optical devices, you are actually changing the optical. You are changing the optical confinement factor. You are changing what is called as the optical confinement factor. Optical confinement factor means the amount the amount of light that is being carried by the core. So if the core is carrying all the signal, then you would say that, so in literal terms, you would say that you're actually sending information signal, you're sending 1. So there are basically 3 mechanisms by which you can adjust. So if you want to modulate light, that means you will have to modulate this one. So this term has to be modulated. In fact, this parameter will have to be modulated. That means you'll have to modulate the optical confinement factor. So look here, you have a core, and then you have a clad here. You have a clad on the top and you have a clad on the bottom. So let me call this index as N1, this is N2, this is N2. Usually N1 is greater than N2. Now suppose if I make N1 to be less than N, so usually N1 is greater than N2. That means this can actually guide the light. If N1 is less than N2, then this cannot actually act as a light, this cannot actually act as a waveguide. So basically you are going to change the optical confinement factor. In other words, you are going to change the refractive index of the core. This is what you are going to change. This ultimately means you would change the refractive index of the waveguide core. You would change the refractive index of the waveguide core. So there are basically 3 mechanisms by which you can do all these functions. One is called as the electro-optic effect, where you apply an electric field. So this is your control signal. So you cannot do it for free. You'll always have to spend some energy. So you'll have to apply some electric field. In fact, this would be a control signal. This would be a control signal, or this could be your information signal. So depending upon your information signal or your control signal. So information signal, so whenever I use information signal, so that is used in the context of a modulator. Whenever I am using a control signal, I am going to use in the context of an optical switch. So depending upon the control signal or depending upon the electric field what you have applied, you can change the refractive index of a material. So the refractive index, if it has a dependence, if it has a linear dependence on the applied electric field, so E is the applied electric field, I would call this effect as the Pockels effect. I would call it as the Pockels effect. Whereas if the change in the refractive index has a quadrature dependence on applied electric field, I would call it as the Kerr effect. So in fact, there are certain materials whose refractive index can be changed by applying an electric field. So those materials are called as electro-optic materials. They are called as electro-optic. They are called as electro-optic materials. And modulators, optical modulators or optical switches, which utilizes an electro-optic material for changing the direction of light or for changing the refractive index of the material, those kind of modulators are called as electro-optic modulators. So they are called as, so simply use this prefix, electro-optic modulators. Now there is another effect which is commonly found in 3-5 semiconductors. So in fact, this is the effect which is found in 3-5 semiconductors. So this is the effect which is called as the electro-absorption effect. Electro-absorption means you apply an electric field, the material will absorb light. So if you have a signal that is being applied, if you have a control signal that is being applied, that control signal will cause the semiconductor material to absorb light, and thereby you will not be able to send the information signal. If you don't apply a control signal, the material does not absorb the light and you can send the information signal. Therefore, the receiver would receive as 1. So this kind of effect is what is called as electro-absorption effect, which is commonly found in 3-5 semiconductor based materials. And those kind of modulators are called as electro-absorption modulators. Now you also have a third effect where you can change the temperature. You can increase or you can decrease the temperature accordingly. You can change the refractive index of the material. Yeah. Hello?
Nothing, sir. You can continue the presentation.
Okay. Yeah, so there are certain materials where you can change the temperature. You can either increase or decrease the temperature, and accordingly, you can change the refractive index. Those kind of materials are called as thermo-optic materials. The effect is called as thermo-optic effect, and the modulator or the switch is called as a thermo-optic modulator or a thermo-optic switch. Now, unfortunately, because of the presence of temperature, because you will have to heat the material, we generally don't prefer to work with these kind of materials. And also the electro-optic effect, in fact, the electro-optic materials, the materials which show this electro-optic effect, they one of the most commonly used material is a material called as lithium niobate, LiNbO3. So it's a dielectric material whose refractive index can be changed by applying an electric field. Now, if you look at if you look at the components of an optical transmitter, you would see that the optical source, which is a laser or an LED, is usually made of 3-5 base semiconductor material. Is usually made of 3-5 base semiconductor material. So a laser and an LED, they are usually made out of 3-5 base materials. The receiver, at the receiver side, the photodetector will also be usually made out of 3-5 base semiconductor materials. But if you are going to use an electro-optic material, or if you are going to use an electro-optic modulator, unfortunately, the material is going to be made of lithium niobate, and therefore, if you want to integrate this, if you want to package the entire device on a single substrate, so probably you might have in yesterday's talk on device packaging of photonic components, you might have understood the advantage of working with materials of similar type, of same type. So it is always advantageous to construct devices made out of same material so that the device packaging becomes very easy. So unfortunately, whenever you are using this lithium niobate material, because it is not made of 3-5 material, you cannot unfortunately package it on a single substrate. And therefore, from the integration perspective, 3-5 base semiconductor materials are going to have significant advantage. And therefore, for the remainder of our lecture, I would be focusing only on materials that are based on I would mostly focus on 3-5 base modulators and devices. Okay, so I explained that you can have what is called as a direct modulation. Direct modulation is this one, what I had shown here. You simply change the current, you can change the light output power. You directly change it. That is what is called as the direct modulation. Now direct modulation, there are certain advantages. The advantage is that it's very simple. All you have to do is simply change the drive current of a light emitting diode or a laser. But the disadvantage is that whenever you change, so we are talking about a laser diode. A diode is a junction which is constructed out of a p-type semiconductor and an n-type semiconductor. You have a depletion region between p and n where the electrons and holes recombine, and that recombination would result in photon. So you are going to get a photon. So this depletion region is actually the waveguide, is having a higher refractive index, and that depletion region acts as the waveguide. Now, unfortunately, what happens is, if you try to, now you want to send ones and zeros, and accordingly you're applying a voltage. You're applying a voltage in the form of a 1 and a 0, 1 0 1 0. So you're going to apply a digital pulse. You're going to apply a digital pulse like this. So every pulse corresponds to 1. The absence of pulse corresponds to 0. So it is this pulse, it is this information signal which is being sent, which is being given to the laser diode. So anytime you apply a voltage, what happens? The holes from the p side and the electrons from the n side gets injected inside the depletion region of this diode, because of which you have a change in the electron carrier density or the electron density. And whenever you want to send a 0, If you want to send a 0, you should not be applying a voltage there, and accordingly the injected carriers inside the depletion region will have to decay. That means their numbers will have to come down. The presence of carrier indicates 1, the absence of carrier indicates a 0. So every time you are turning on and turning off the laser diode, at each instance you are actually injecting electrons and holes. You are injecting these carriers. So because of this carrier injection, because of this change in the carrier density, unfortunately the refractive index of this depletion region would also change. That means because of this injection in electron hole density, the refractive index of the core unfortunately changes. That means the refractive index of the laser diode changes. The laser diode, please remember, the laser diode is supposed to emit only at one particular wavelength. The laser diode should be always emitting at lambda naught. But because of this injected carrier density, there's a change in the refractive index of the laser cavity, and because of which this lambda naught would slightly deviate. There is a slight drift in this lambda naught. This would become either lambda naught plus or minus delta lambda. There's a change in the wavelength at which the laser diode operates. So this change in the this drift in the laser wavelength because of the injected carrier density is what is called as wavelength chirping, or is more frequently or more commonly called as, this is what is called as frequency chirping. So this phenomena happens when you try to when you try to turn on and turn off the laser diode at very high speeds. That means if you are exceeding something like 10 gigabits per second. So if you are turning off and turning on the laser diode at speeds exceeding 10 gigabits per second, you would see that there is a significant change in the refractive index, and accordingly you have a significant change in the emission wavelength of a laser diode, and this phenomena is called as frequency chirping. In fact, this is a very serious phenomena because please remember, the photo detector is designed to receive only lambda naught. If it receives lambda naught plus delta lambda or lambda naught minus delta lambda, the photo detector will not be able to decide what it has received, and accordingly the photo detector will make an error. So you would always want to, so nowadays we always want to send information at very high speeds. You always want your internet speed to be very high, right? So that means you always want to increase, you always want to send signals at speeds exceeding 10 gigabits per second. And when you are sending signals at speeds exceeding 10 gigabits per second, this frequency chirping happens, which means that unfortunately direct modulation is not a feasible modulation technique, and therefore we go for what is called as the external modulation scheme. This external modulation scheme is what is being shown here. In this case, the laser diode is always kept as at a fixed bias. A fixed bias means you always keep the laser diode on. So laser is always on. Rather, what you do is you put an external device which is called as a modulator. You have an external device which is called as a modulator. So probably this is made out of 3,5 based material, or this could be made out of lithium niobate material. It could be made out of one of these three, and you would change the property of this modulator so that you at the output you would receive either 1 or a 0. So we are going to, so in our talk we are going to discuss about this external modulation scheme, and nowadays you are all, so nowadays in all modern communication systems we generally utilize only external modulation scheme. Okay, so now we'll come to what is called as an optical switch. So I spoke about optical modulation where you change the property of light. Now optical switching is something similar, but there is a slight difference. Now imagine that you have an optical network and here is a node. Now this is called as a node, or this is a junction. This is a junction. A junction is a place where, so if you look at the road, a junction is a place where two roads meet. So once you reach, so imagine that you are driving your car, you are reaching your junction and you would like to go to the left. So accordingly, what you would do is you would turn the steering so that you can go to the left. Or if you want to go to the right, you turn the steering to the right. Now, fortunately, in the case of, so whenever you are driving your car, since you have the intelligence, you have the right to decide whether you can go to the left-hand side or to the right-hand side. Now, if you think about photons, now photons, unfortunately, does not have that intelligence. Once it reaches the junction, you will have to tell to the photon whether it should go to left or it should go to the right. So how do you do that? You do that by a device which is called as an optical switch. So you use what is called as an optical switch. So you can use an optical switch at this place B, and by applying a control signal, so imagine that you are having, so you have a red signal, or you have a red signal and a green signal that is simultaneously coming at B. Now I want the green signal to go to D, I want the red signal to go to C. So that can be done by an optical switch where you apply a control signal and you can decide whether the signal will go, the red signal will go to this side or to this side. So any device, so switching, in fact, the definition, the textbook definition of switching is the process by which you spatially change the location of an optical signal in accordance to a control signal. And any device which does this phenomena, which does this function, is what is called as an optical switch. Now, in the case of electronic signals, the most commonly used switch is a transistor. So you can use a transistor which is properly biased. So I can apply a VCC there. I can have a base resistor. I can have a collector resistor. I can apply, so I can ground this terminal. I can apply a signal to the base of the transistor, and accordingly I can decide whether a current should flow through the collector emitter junction. So whether I want a current to flow through this path can be decided by applying a control signal here. So you might all of you might have studied about this kind of switch. So this is an electronic switch. So what does it do? You apply a control signal, you can decide whether you can have a current flow or not. We also do almost the same procedure here. You apply a signal, you apply a control signal at this point B, and then you can decide whether the optical signal should flow through this path or to the other path. Okay, so we'll go to what is called as a phase modulator. So before I discuss about amplitude modulation, I would like to discuss what is called as a phase modulation. So phase. So you can have, so here I have shown a device, I have shown a material which is made out of lithium niobate. So this white region is made out of a material called as lithium niobate, but this green region what you see here, so this is the cladding. This is the cladding. This green region what you see here is the core. So this has a higher refractive index. So how do you make this green region? Is by a process called as proton implantation. Proton implantation, or I can actually diffuse titanium metal. So I can diffuse some titanium metal. I take some titanium, I just diffuse inside this material, and thereby I can create a region whose refractive index is slightly greater than the surrounding region. So how you do this? Probably you might hear about this lithium niobate waveguides in tomorrow's lecture when you hear about photonic integrated circuits. So anyway, this region, this green region, has a higher refractive index. Now what happens is, on the adjacent side, I have two electrodes that are being placed. So this is one electrode. This is a metal electrode. This is the other metal electrode. And between this metal electrode, I can apply an electric field. So here I can connect a battery. I can connect an I can supply an electric field. And remember, the electric field always runs from positive to negative. So you have these electric flux lines which penetrates through this waveguide. And this is an electro-optic material, which means whenever you have a presence of an electric signal, whenever you have the presence of an electric field, the refractive index of this green region would change. And accordingly, so whenever you have a change in the refractive index, accordingly, the phase of the signal that is flowing through, the phase of an optical signal which is flowing through this waveguide will also change, and that change is given by this particular mathematical expression. So you have an expression which governs the change in the optical phase depending upon the applied electric field. So here L is the length of this electrode. This D, so this D is actually the spacing between the electrode. V is the applied electric field. V is the applied voltage. N is the refractive index of this material, and this R is called as, the electro-optic coefficient of this material. So that's a figure of merit which tells you, for a given applied electric field, how much is the change in the refractive index. It's a figure of merit. So you would always like to work with materials which can give you the largest change in the electro-optic coefficient for the least applied electric field. All right, anyway, so I have an input light, I have an input signal, and at here I have the output signal. So what happens is, if I don't apply an electric field, there is no phase change. But if I apply an electric field, there is a phase shift. There is a phase shift. So there is a phase shift. Now, electromagnetic signals, or photons, or electromagnetic signals, they have an electric field, and electric fields are always vectors. That means, so imagine that I have an electric field. So let me say E1 is given by E0 cos of omega t, and I have another signal E2 which is given by E0 cos of omega t plus pi. That means, imagine that I have two signals, but their phase difference is pi. There's a phase difference of pi between them. So if they have a phase difference of pi between them, and if I recombine these two, if I try to recombine these two, so recombining these two, or combining these two in the context of optical signals, you call it as you call it as interference. You call it as interference. Interference is the same as beating in electrical communication. You have a local oscillator which beats the signal with the information signal. So likewise, you are actually mixing these two signals, or you are actually trying to combine these two signals. So if the relative phase difference between these two signals is of the order of pi, that means they are opposite in phase. What results is, you have what is called as a destructive interference. You have destructive interference. You have destructive interference. So when you have destructive interference, at the output you don't get any light. So I'm just giving you some basic information. But suppose the relative phase difference is of the order of 0 or 2 pi. If this phase difference is 2 pi, then they would recombine. You would be having a constructive interference. So you would be having constructive interference. You would be having constructive interference. So you could exploit this phenomena in what is called as a Mach-Zehnder interferometer modulator. So earlier this was also one of the most commonly used optical modulator configurations. So here you have an incoming wave. This wave gets divided into two. And imagine that you are not applying any electric field. So if there is no electric field, there is no phase difference between the wave that is arriving at D. So A and B has the same phase difference, or they have the same phase, and accordingly they recombine, and therefore they constructively interfere. Therefore you are going to get, so whatever you are sending here, so here I have sent some signal, so here you are getting the same signal over there. But once you apply a voltage, so now I am applying a signal, I'm applying a control signal, or I'm applying my information signal. Because of this information signal, there is a phase difference which happens at this waveguide and also at this waveguide. So here I'm applying a positive electric field. Here I'm applying a negative electric field. The electric fields are in opposite direction. So because of which, the two waves that are arriving at D, they have a phase difference of pi. And accordingly, whenever you have a presence of signal, they destructively recombine, and as a result, you will see that at this point you have no information signal. There is no signal there. There is no signal there. That means here you are getting 1, here you are getting 0. That means you are actually modulating now. So this can actually act as an optical modulator. In fact, if you combine these two, if you have a combination of this, you can also have what is called as an optical switch. So in this case, this acts as an optical modulator, because depending upon this control signal at the output side, you are getting 1 or a 0. So this configuration is called as a Mach-Zehnder. It's called as a Mach-Zehnder interferometer. So this device is called as an interferometer. Because this exploits the phenomena of interference, the combination of two optical signals, and therefore you get either 1 or a 0. So this is called as a Mach-Zehnder interferometer modulator. So yeah, so this slide basically explains what I have just explained before. So when you have a relative phase difference, they destructively interfere, you don't get any light. But if you have if there is a phase difference of there's a phase difference of 2 pi or 0, you have what is called as a constructive interference, and accordingly you can modulate the optical signal. Now you can also have optical waveguides. Now you can also have what is called as modulation by exploiting two waveguides in close proximity. Now imagine that now this is the cross section of a waveguide. So there are two waveguides that are present. So you have a waveguide A and you have a waveguide B, and imagine that at the beginning the refractive index are the same. That means NA is equal to NB. Sorry, NA is equal to NB. They both are same. The refractive index is the same. So this is the side view of the optical device, and this is the top view of the optical device. And imagine that I'm launching my light from this point. So from this point I'm putting my light. I'm launching light from this side. So here I'm launching light, and these two waveguides are in close proximity. Now in any waveguide, so whenever you have a waveguide, you have a core and a cladding, which means majority of the signals, majority of the photons are being confined inside the core, but there is some portion of the optical signal which is being confined inside the cladding. So this tail what you see here, is what is called as the evanescent tail. This is called as the evanescent tail, the optical signal which is confined inside the cladding. In fact, their amount will be extremely small in normal waveguides. Now imagine that these two waveguides are kept far apart. If they are kept far apart, this the signal that is there inside the waveguide, this waveguide will not interact with this waveguide, because this waveguide and this waveguide, they are kept far apart. Their distance is very, very large. But once these two waveguides are kept in close proximity, you call those waveguides as coupled waveguides. So once these two waveguides are kept in close proximity, it turns out that the signal that is being confined in the first waveguide will start coupling to the second waveguide. That means if I launch the signal at this point, the signal will propagate along this direction, but also a portion of the signal will couple to this waveguide. It will start coupling to this waveguide, and after a certain distance, you will see that the entire signal which was launched here would now be appearing not at this point, rather at this point. So by default, if I launch the signal here, the signal would appear at this point. All right. Now what I'm going to do is I apply an electric field. I apply an electric field to one of probably I apply an electric field to this waveguide. So here I put an electrode and I apply an electric field. So because of an application in electric field, there's a change in the refractive index. That means now NA is not equal to NB. That means the light cannot couple to the second waveguide, and therefore this coupling is prohibited, and therefore whatever light I launch here will ultimately appear at this point. So in fact, you can construct an optical waveguide, you can construct a modulator like this. This modulator is what is called as a directional coupler modulator. So here is an image of a directional coupler modulator. So by default, I am launching the light here. The light would now appear at this point if there is no applied electric field here. So once I apply an electric field, so this is the cross section. Once I apply an electric field, there is a change in the refractive index in one of the arms. So this is called as arm 1 and this is called as arm 2. So it's called as arm, ARM. It's called as arm. So there is a change in the refractive index of one of the arm, and accordingly once I apply the electric field, the signal instead of appearing there, would now appear at this point. The signal would be appearing here. So now this device is called as a directional coupler modulator. Now this device can also act as an optical switch. Why it can act as an optical switch? Because depending upon the control signal, the light is appearing either at this point or at this point. So this can act as an optical modulator also, because if I'm looking at this point, if my photodetector is at this point, if no signal there, if I'm sending a 0, if no signal there, I'm getting signal here. If there is a signal there, if I'm applying a signal, this signal appears there. Therefore, I'm getting 0 over there. So if I use one port, it acts as an optical modulator. If I'm looking at this port, this can act as an optical switch, because I can switch the signal either at this point or at this point. So this kind of modulator or this kind of device is called as a directional coupler modulator. This can also act as an optical switch. This can also act as an optical switch. Okay, so I think we'll have a break here.
Yes, sir. We can take a break for 15 minutes.
Yeah, I would request not to shut down the meeting, because again, some of the settings might go bad and we might lose the time. So please don't end the meeting.
Okay, sir.
Yeah, thank you.
Participants, we can take a short break. You don't want to leave the meeting, okay? The same session will be continued at 11:45.
Yeah, I don't want. Yeah, we'll once again start this at 11:45. Thank you.
Okay, sir. Thank you.
This conference will now be recorded.
Okay, shall we begin?
Yes, welcome
Shall we
back to the
resume?
same session. Sir, you can continue.
Okay, so I hope I am audible enough.
Yes, sir, you are audible.
Okay, thank you. Yeah, okay. So we discussed about some of the conventional optical switch and modulator configurations that are used in optical communication systems. So one was the directional coupler modulator. We just saw that. The other one is the Mach-Zehnder interferometer configuration. In fact, these two configurations, they commonly use what is called as the electro-optic effect for switching the signals or for modulating the signals. Now, there is another kind of configuration which I have not discussed the configuration, but the configuration is what is called as a waveguide modulator. Is called as it's called as the waveguide modulator. So I hope you can see the screen.
Sir, it is visible.
Okay, thank you. Yeah, okay. So this configuration is called as the waveguide type. It's called as a waveguide type because you basically have a core and a cladding. So this red region, this black region. So this is the core. The other two regions are the cladding. Now, in the case of a waveguide type optical switch or a modulator, we use what is called as the electro-absorption effect. So we just discussed what this electro-absorption effect is. You apply an electric field. So the application of electric field would cause a change in the absorption. So the absorption of the waveguide core, of the core material, would change. So that phenomena is called as electro-absorption. So you apply an electric field and the absorption of the waveguide material would change. So if the material absorbs light, so you imagine that I am putting light from here. From this side I am putting light and here is an electric field. So if I apply light, this black region would absorb all the photon. Therefore in the output you don't get any light. Therefore I am going to get a 0. Whereas if I don't apply any signal here, this material will not absorb any light. So whatever light you are launching from this side will appear at the output, and therefore you are going to get a 1. So depending upon you apply or not apply the electric field, the material's absorption coefficient would change, and accordingly the output intensity can also be changed. So the waveguide configuration, what are commonly used for constructing these kind of modulators, is what is called as the waveguide type, and the effect is called as the electro-absorption effect. Now, one of the common feature for all these, now in fact this electro-absorption effect is commonly found in 3-5 semiconductors. So that's a fundamental difference. Whereas this electro-optic effect is commonly found in a material which is called as lithium niobate. So from the integration perspective, electro-absorption modulators are more advantageous because the laser is made out of 3-5 semiconductor material. Now just outside the laser you have a modulator here. You have a modulator, and if you are using waveguide type, this is 3-5 anyway. This can also be 3-5. That means you have an added advantage because the laser and the modulator can be integrated on the same chip. So from the perspective of monolithic integration, monolithic here means the same material. So same material. So from the perspective of monolithic integration, electro-absorption based modulators are always advantageous. However, there is a common drawback for all the conventional optical switches and modulators. The drawback is that they all have a very large device size. So the device size is typically of the order of few millimeters, something like 2000 to 3000 microns. It has a very large device size. So 2000 to 3000 micron is something like 3 millimeter. That's the size of one optical modulator alone. Now, if you compare this, now you might think, well, 3 millimeter is not a big thing. But if you compare the size of an electronic switch, which is nothing but a transistor. So if you have a transistor as a switch, and if you look at the size of the modern day transistors, it is something of the order of something like 50 nanometer or 100 nanometer. The size of a typical transistor, of a modern day transistor, is extremely small compared to an optical switch. And therefore, since you always want to match the integration what you can achieve in the case of optics with that of electronics, you would see that the devices which are having large size or long device length is not advantageous for optical integration, and therefore you want to use something different. You want to use some new configurations which can help in realizing large scale integration. So you want to have large scale integration. So large scale integration means you want to integrate large number of devices on a small area. That is what is called as large scale integration. So for that configuration, with that in mind, so there is a particular configuration which is called as the ring resonator configuration. So I think in yesterday's lecture in the optical sensors, you might have you were introduced with this. You got introduced with this kind of device structure. So this is called as a ring resonator. So it's a resonant device. Resonant device means it usually supports only one particular wavelength. That is what is called as resonance. Or any resonant device. Any resonant device will have a maximum response at a particular wavelength. So it will have the peak response at a particular wavelength. In fact, electronic oscillators, all the oscillators what we have studied, they are all resonant devices because they always operate at one particular frequency. Again, so this is also a resonant device. Resonant device means it supports only one particular wavelength. So the configuration is like this. You have a straight waveguide. So you have a straight waveguide which is kept in close proximity. So this straight waveguide is kept in close proximity with a ring. So this is the waveguide. This is the ring. And the distance between them is typically of the order of 100 to 300 nanometer. That's the gap between them. The gap between the straight waveguide and the ring is typically of the order of 100 to 300 nanometers. And we have already discussed in the case of directional coupler modulators that whenever you have two waveguides with the same refractive index, and if they are kept very close, if they are evanescently coupled, the light that has been launched in one waveguide can be coupled to the other waveguide. You call it as the evanescent coupling. So you can have, though you launch signal only in one waveguide, it can ultimately get coupled to the other waveguide because they are very close. If they are kept very far apart, they don't couple. They cannot. You cannot have power exchange. So in this case, because they are in close proximity, you can have power exchange between them. That means photons can go from here to there. Photons can also go from the ring to the waveguide. So the amount of light that can get coupled, the amount of light that can get coupled to this waveguide is actually decided by the spacing between them, and is usually represented by a parameter which is called as the coupling coefficient. It's called as the coupling coefficient. So if I'm launching 100 photons, 50 photons are getting coupled to the ring, and 50 photons are going to the 50 photons are going straight, then I would say that the coupling coefficient is 50%. the transmission coefficient is 50%. So I would say that I'm having a 50-50 coupling. All right. Now imagine that now this ring has a particular radius which is given by n. The refractive index is n. So imagine that I'm launching a bunch of optical signals to this waveguide. So let's say lambda 1, lambda 2, and lambda 3. Now usually nothing would happen. Whatever signals you put here would all appear at the output port. However, if you have a very special condition which is called as the resonant condition, which is given by m lambda 2 is equal to 2 pi r into n, where m is a number, n is the refractive index of the ring, r is the radius of the ring, and lambda 2 is one of this wavelength. So from a series of signals what you are launching, one of the wavelength satisfies the resonant condition, and therefore this resonant signal will couple to this ring. So instead of this, this resonant signal, instead of going straight, would get coupled to the ring, and it will keep on rotating inside the ring, and ultimately this signal will get coupled back and it will go straight. So this structure can act as what is called as an all-pass filter. All-pass filter. All-pass means whatever signals you are launching inside will all appear at the output port. So it passes all the signals. Therefore, you call it as an all-pass filter. However, if I put a second waveguide here, if I am putting a second waveguide here, then what would happen is this resonant signal lambda 2, which satisfies this particular resonant condition, this lambda 2 would now get coupled to this straight waveguide, and this lambda 2 will ultimately appear at this D port. This will actually appear at this point. So therefore, if I'm looking at the transmission spectrum, so I would call this as the input port, this is the transmission port, this is the drop port. This is the drop port, and this port is kept idle. So if you want, you can add other signals. So I would call this as the add port. So if I'm looking at the spectrum of the transmission port, you would see that the resonance signal is actually missing at this point. That's why you see a dip over here, and whatever is missing here would appear at the D port. So whatever was missing would be appearing at this point, so that if you add the power at this point and this point, you would actually get the power at this point. So if you have a condition where this power plus this power is equal to this power, then I would say that this coupling is actually lossless. So I would call it as a lossless coupling. So I would call it as lossless coupling. But however, so please remember, all these waveguides, they have a rectangular shape. So they all have a rectangular shape. So we have earlier seen that when you are making waveguides, if the rectangle is not exactly a rectangle, there are some corrugations there, then the signal will actually start leaking. You will lose some of the photons, which means if you add these two numbers, you will not get this number. Then you would say that the coupling is a lossy coupling. Anyway, so these kind of structures, so they are called as so this configuration is what is called as a ring resonator. And there are certain advantages for this. The advantage is that it's a planar structure. So planar structure, we already saw what are the advantages. So all the semiconductor laser diodes, LEDs, optical modulators, they all have a planar structure. The other advantage, in fact, the biggest advantage is this size. That means this is the real estate, this is the footprint of this device. This size can be as small as something like 10 microns or even 5 microns. So this can be very small. So we have just seen that the conventional optical modulators and switches, they had a size typically of the order of 3000 microns. The extreme case is 3000 microns. But compared to that, this ring resonator device is going to have a very small footprint. That means you can actually integrate. So this is very suitable for, extremely suitable for large scale integration. So you can integrate a large number of devices on a small substrate area. Of course, the other advantage is you can construct this out of different materials. For example, you can use lithium niobate. You can construct it on glass. You can construct it on silicon and also on 3-5 semiconductors. So you can construct these devices. So it has lots of advantages and it can be constructed on a wide variety of material systems, and therefore these kind of configurations nowadays are getting more attractive for people. So for the remainder of our lecture, we will focus on this particular configuration. So this is a waveguide. So this is the configuration what we are going to study. It's called as the ring resonator configuration. Now there are different in fact, these rings can be placed in different configurations. You can have, so if you have a configuration like this, if you launch only lambda2, this lambda2 will be sent in the backward direction. Whereas in this particular case, if I put two rings here, so I have the first ring, so this is the ring 1, this is ring 2. So in this case, if I put lambda2, this lambda2 will couple to the first ring, second ring, and will appear at this point. So in fact, this kind of configuration, this configuration is called as a double ring configuration because you are having two rings here. So this double ring configurations, they have certain advantages in the sense that the launch signal, so this is the input side, the launch signal and the resonance signal or the drop signal, they are flowing in the same direction. And therefore, you can put one more ring here. You can actually put another ring here. You can put one more ring here. So if you want to cascade this, so let's say that I want this lambda2 to go to some other user. Let's say there is a user here, and I have another user here, and I want to launch lambda1. So let me put lambda1 here. So this lambda2 has to go to this user, lambda1 has to go to the other user. So in fact, I can put this lambda1 here. This is the add port. It will couple to this ring, couple to the second ring, and it will ultimately go to the other side. So from the interconnect point of view, these double ring resonators are better because the light is always flowing in one direction. So remember, light always, you always want the light to flow from transmitter to the receiver, not to the backward direction, not from receiver to transmitter. You always want in a forward direction for the light to flow, and that is possible in this particular configuration. All right, so we'll focus, we'll see some details about this double ring configuration. Now in this double ring configuration, so imagine, so I'm launching light here. Ultimately my aim is I'm putting some light here, I'm launching the light, so some light would appear here. So there is some light here, there is some light here, and there is some light over there. So there is some light over there. So if you know the electric field, so in the context of light, you're always interested in calculating the optical power. You want to calculate optical power, or in other words, you want to calculate the intensity. And intensity is nothing but the electric field multiplied by the complex conjugate of the electric field, or in other words, the modulus of electric field square. So if I launch the light here, if I know what is the electric field amplitude at this point and at this point, then I can actually calculate what is the optical power that is present at this point and the other point. So how do you do this? So you do this by this process. So please note that there is a coupler over here. So this box region, what you see there is a coupler. It's actually a coupler. So the photons arrive at this point. Photons arrive at that point. So some photons would go straight. The remaining photons will be coupled to this ring. So the amount of photons that are getting coupled to this ring is denoted by this coupling coefficient. And the amount of photons that are being propagated directly, that is getting transmitted, is given by this particular coefficient, the transmission coefficient. So if I look at the electric field amplitude at this point A1, the electric field, the photons that are coming here is actually the photons that are coming from this point plus the photons that are going in this direction. All right. So accordingly, I can write the electric field amplitude at this point even as, which is given by this expression. The light, that is the amplitude of the light that is coupled from here plus the amplitude of the light that is going in this direction. So the amplitude of the light that is going in this direction is given by this term, and the amplitude that is getting coupled here is denoted by this term. Now the photons reaches here. Now what does the photon do? It will go from A1 to B1. That is how it flows. Photons come here, gets coupled, moves from A1 to B1. So some of the photons would go in this direction, the other photons would get coupled to this ring. So from A1 to B1 there is no coupling. There is no coupling, but these photons are simply flowing in this direction. It's actually flowing in this direction. So it is flowing from A1 to B1. So whenever photons are propagating through a waveguide, there are two things that can happen to that photon. The first thing is that there is always an associated phase change. There is a phase that is getting added to it. So whenever the photon propagates through a medium, it accumulates phase, which is decided by the refractive index of the medium. So the phase that is attained or accumulated, the phase is proportional to the refractive index of the medium and also the distance what it travels. So this is it's a basic concept. So the phase is proportional to the phase that is accumulated. The more it propagates, the more phase it gets accumulated. So the phase is proportional to the refractive index of the medium and also the length for which it propagates. So it accumulates a phase. The second thing is, as the signal is flowing through a waveguide, the signal can also be lost in the process of absorption. So signal accumulates a phase, signals also get absorbed. So how do you find the absorption? How do you find this amount of signal that is getting absorbed? So you would like to know what is the absorption coefficient of this particular material or this particular waveguide. So if I assume that the absorption coefficient is alpha, and if L is the length for which the signal is getting propagated, then the electric field amplitude, which is given at point B1, is given by the amplitude of the signal at A1 multiplied by a phase factor and an absorption factor. So you can repeat this process for the entire rings, and ultimately you can arrive at the power that is appearing at the transmission port. So I would call this as PT, the power that is appearing at the transmission port, and I would call this as PD, which is the power that is appearing at the drop port. So that means if I look at the ring resonator configuration, if I look at the power at the transmission port and the power at the drop port, you will see that these two powers, they are a strong function of the refractive index of the ring and also the absorption coefficient of the ring. So by default, if I launch the resonance signal, if you have a ring resonator configuration like this, if I launch a resonance signal lambda2 here, this lambda2 by default, it should be appearing at this drop port. If the coupling is lossless, so whatever power I put here should all be coming at this point. So this means, and since this is a strong function of n and alpha, that means the index of n is the refractive index of this ring, and alpha is the absorption coefficient of this ring. So that means, if by some means, if I can change the refractive index or the absorption of this ring, if I change the refractive index of the ring or the absorption coefficient of both the rings, then what happens is the lambda2 which was originally appearing here would now appear at this point, because the light which is appearing here should either come here or it should come there. So if it is not coming here, then it should be going there. So by changing the ring refractive index or the absorption, the power, the signal which is appearing at this point would now appear at that point, which means that you can actually realize a micro ring resonator optical switch or a modulator where you can change the refractive index, you can change the absorption of the rings, or you can change the refractive index of the ring. And so how do you change these two? You can apply an electric field. You apply an electric field, you can change the refractive index or you can change the absorption. Thereby, the light can be switched from this point to that point. Or in other words, you can also modulate the intensity of light. So if you are looking at this point, so I am just focused at this point. So I am looking at this point. So by applying a voltage, if no voltage is applied, light is appearing here. That means I am getting a digital one. When I apply a voltage, there is some change in refractive index or in absorption. We will see that, because of which the light cannot get coupled to this ring. The light goes directly. That means no photons are appearing here. When I apply an electric field, that means I am getting a 0 there. And therefore, this would act as a modulator. Whereas, if I'm applying a control signal, the light can be switched from this point to there. So when no signal is there, light appears here. When signal is there, the light appears there. That means I'm switching lambda2 between the drop port and the transmission port. So therefore, this device can also work as, a switch, and it can also work as a modulator. So it can work as both devices. So we'll first see how so before we go into details, so I said that the rings and the waveguides, they are getting coupled. So this kind of coupling is called as evanescent coupling. So you can have two kinds of coupling. One is called as, this is called as lateral coupling. So you have two straight waveguides. This red region, what you see here, is actually the core. So this red region, so this is the core. This has a higher refractive index. So you can have a substrate on which you can have a rectangular waveguide, a ridge waveguide, So if I am looking from this direction, the cross section would be looking something like this. This is the waveguide, and then you will see a red region here. This is the core. So this red region, what you see there, is actually the core. The other two regions are the cladding. So this is clad. So this is also clad. So these two are cladding. The other one is the core. So for the straight waveguide and the ring, the core region is along the same plane. I hope you can imagine that. So this is called as lateral coupling. It's also called as side coupling, because the ring and the waveguide, they are kept side by side. They are kept adjacent to each other. You can also have a different kind of coupling, which is called as the vertical coupling, where the ring sits exactly on the top of the straight waveguide. So in this, the coupling coefficient, I told that if I put 100 photons at this input side, 50 might get coupled to the ring, 50 might go straight. So that I have a 50-50 coupling. So this coupling coefficient is actually decided by the physical spacing between them. So smaller the spacing, larger is the coupling. So here in the case of lateral coupling, the coupling coefficient is decided by the spacing between the straight waveguide and the ring. Whereas in the case of vertical coupling, the gap between the straight waveguide and the ring decides the coupling coefficient. So practically, when you make the device, it turns out that vertical coupling is advantageous because you can precisely control the coupling coefficient. Okay, so practically this is the more preferred configuration. So here is an image of a single ring resonator, a double ring resonator, and a triple ring resonator. So and this is how the output response would look like. So this is how the output response would look like. Anyway, so this is a closer. This is an microscopic image of a ring resonator. In fact, this kind of configuration is called as a racetrack resonator. A racetrack resonator. So we discussed about a configuration where you have two parallel waveguides. You have two parallel waveguides, and then you have a ring there in the form of a circle. So if you have a ring and a waveguide, then there is only one plane. There is only one point where you have a coupling interaction. You have an interaction between the straight waveguide and the ring. So fabrication wise, this is more challenging. Whereas in this case, rather than having a circular configuration, you can have what is called as a racetrack configuration like this. You can have a racetrack configuration, and accordingly, this gap, you can have a slightly higher tolerance in fabrication. So this is more easier for you to fabricate and then characterize. So racetrack resonator is more easier. Okay, so my student actually carried out some electromagnetic simulations of how the signals propagate. So if you have a resonant signal, so this is so here you have two rings. So I am putting lambda naught, and resonant condition means the refractive index of the straight waveguide and the refractive index of the ring, they are the same. So the refractive index is all same. And the absorption coefficient of this ring and the waveguide is also the same. And therefore, you will see that whatever signal I am launching here, almost everything is appearing at this point. So lambda naught is coming at this point. You call it as the resonant condition. Non-resonant condition happens when you change the refractive index or the absorption. So alpha or n. Alpha is the absorption coefficient, n is the refractive index. You change any one of these, and you would see that whatever light I'm putting here, almost all the light would be appearing at this point. So here you don't see any light there. So light which was originally coming here has now been switched to this point. So so in fact you can actually solve Maxwell's equations for these kind of waveguide structures, and you can actually plot the electric field amplitudes. So nowadays there are commercial softwares which can do this. Okay, so we'll see the case where, so I said that micro ring resonators can be made out of different materials, but of which we are going to study about micro ring resonators that are made out of 3-5 semiconductors. So you can construct devices made out of 3-5 semiconductors. And so I also said that you can change alpha or n. You can change the absorption coefficient, or you can change the refractive index of the material. So absorption coefficient can be changed. That switching phenomena is what is called as electroabsorption. So we are going to discuss about a micro ring optical switch or a micro ring optical modulator made out of 3-5 semiconductor materials, where the absorption coefficient is changed by electroabsorption, is changed by electroabsorption. Electroabsorption means you apply an electric field to the semiconductor material. The material changes the absorption, or the material absorbs the light, and thereby you have a change in the absorption coefficient, and accordingly the light can be switched from one point to another. So we'll see that. So we'll study about the structure. So how do you construct 3-5 semiconductor optical switches? What is the structure, and what factors would decide the device performance, and what are the switching characteristics? So whenever you talk about device performance, so a switch can have two states. So I'll give you some basic introduction about switch. Any switch, a switch can have two states. The first state is called as the off state. The other state is called as the on state. So off state means there is no signal, and on state means you have a signal. And how do you make it on and off? You have a control signal. So there is a control signal now. So there is a control signal. There's a control signal, which is in fact an electrical signal, which would decide whether you get off, which means no photon, or which is on, which means you have a photon there. And you have a control signal, which is an electrical signal, which is an let's say this is a voltage. So one of the figure of merit, or the device performance, is called as something called as the contrast ratio, or simply it's called as a contrast difference. You can define in any terms, but I would call it as contrast ratio. It's called as contrast ratio. That means I find out what is the optical power. So what is the power? What is the number of photons that are received when the switch is off? And I find out what is the ratio between what is the ratio when I am receiving photons. So there will be a ratio. So this ratio, which is called as the contrast ratio, ideally should be as large as possible. That means you should be clearly able to distinguish between on and off, or in other words, black and white. It should not be gray. It should be exactly black, or it should be exactly white, so that you can have a clear distinction between 1 and 0. So higher the contrast ratio, greater will be your ability to distinguish between 1 and 0. All right. So this is the first device performance. The second device performance is decided by, in fact, there are other device performances, there are other performance parameters also. The other device performances, I told that there is a control signal, there is a voltage. There is a voltage which causes the signal, which causes the switch to be either on or off. Which means I want the signal, I want the device to be activated. So I want device activation. Device activation. Activation means on or off. I want device activation for the least applied electric field, or the least voltage that is applied, for the least applied voltage. So for the slightest applied electric field, I want I should be enabling the switch, or I should be disabling the switch. So it is just like all of us, right? So we want to do the least amount of work, and we want to get the maximum benefit. So for a student, we all would, if we all are students, we would like to study the least and get the maximum marks. And if you are working somewhere, we would like to do the least amount of work, and we would like to get the maximum amount of salary. So just like that, I'm just giving you an example in real life so that you all can relate. So just like that. So since we humans are extremely greedy, so we want our devices also to be greedy. So we would like to have the least applied voltage, and you want to have the best contrast ratio. So we will see how these parameters are all related. So in fact, this is the switch configuration. So you have a straight waveguide, you have two straight waveguides, and you have two rings. And the straight waveguide and the rings, they are constructed by using a semiconductor structure which is called as a quantum well. We'll see what a quantum well is. So in normal case, what happens is you launch an optical signal. So you launch an optical signal. By default, this signal is going to appear at this D port. So it gets coupled to the first ring, gets coupled to the second ring, and it will appear here. That means from the top view of the switch, if you look at the top view of the switch, the performance would be like this. This is the input port. So this point is the input port. This point is the D port. This is the D port. This is the input port. And I would like to enable the switch. That means I want to apply an electric field. So I can apply an electric field by putting two electrodes. So on the top of the rings, I have two electrodes. I call it as a P electrode. On the bottom of the substrate, I have a single electrode which is called as the N electrode. So this is the N electrode. This is the P electrode. And the cross section would look like a PN diode, or in fact, this is actually called as a PIN diode. So here you have p-doped material. Here you have intrinsic material. That means undoped material. And here you have n-doped material. So this has large number of holes. This has large number of electrons. So this is how the configuration of the straight waveguide as well as the ring would look like. Now what you do is, I apply an electric field on the rings. When I apply an electric field on the rings, so for a quantum well structure, we'll see that very soon. We'll see that when you apply the electric field, and if the wavelength is right, you will see that there is an absorption that happens inside the ring. So there is going to be, so you apply electric field. So you apply electric field. This would cause a change in absorption. Change in absorption. So there will be a change in absorption. Now please note that this change in absorption happens only for the rings, because only to the rings we are applying electric field. The electrodes are present only on the rings, and therefore you're going to have a change in absorption in this ring. Because of the change in absorption in the ring, the light will now not be able to couple to this ring. So this condition happens. So this is a non-resonant condition. This is non-resonant, whereas this was resonant. So in the non-resonant condition, the light will not get coupled to this ring, and accordingly what happens is, this light which was initially appearing at the D port would now appear at the T port. So from the top view, if you are looking, this is the input side, this is the T port, this is the T port, this is the D port. You will see that at the D port you have almost no light, and at the T port you have almost all the light. So this is how the structure works. And for optical communication systems, usually you know that in the case of optical communication system, there are generally two wavelengths that are highly important. So one is the 1300 nanometer signal, the other one is the 1550 nanometer signal. Now this signal is preferred because the optical fiber has the least dispersion. It has least dispersion. It has least dispersion for 1300 nanometer, whereas 1550 nanometer signal is preferred. That wavelength is preferred because optical fibers has the least attenuation. So probably you will study about, you will hear more about these wavelengths in today's afternoon's lecture, where you will be hearing about nonlinear effects in optical fibers and how you can avoid them. Probably you will understand the importance of 1300 and 1550 then. All right. So your switch should be able to support 1300 nanometer or 1550 nanometer, one of these. Now, unfortunately, so I said lot of advantages about semiconductor materials. You can integrate that with a laser diode. In semiconductor materials, you can apply an electric field and you can change the absorption, but there are also certain other drawbacks. So please don't think that semiconductors are the best. They also have some drawback. One drawback is that you will have to properly choose the material composition so that the material can support 1300 nanometer or 1550 nanometer. So you will have to properly choose the material. So material composition is very important. So material composition. So one factor is you will have to think about material composition. So there are not much semiconductor materials which can be used. There are only a very handful of materials. So fortunately, one of the material that can support these wavelengths are what is called as, there is a particular material composition which is called as indium gallium arsenide phosphide. So this is a quaternary semiconductor material because it has 4 elements: indium, gallium, arsenic, and phosphorus. So it's called as a quaternary semiconductor material. So this particular material, so you should be choosing the right combination of material composition. Fortunately, this particular material composition can support 1300 nanometer or 1550 nanometer. So that is good enough for us. So we are going to use this particular material. So so in fact, I said that we don't have much we don't have much material. In fact, you don't have much semiconductor, you don't have much material choices. In fact, you can use only indium, gallium, aluminum, phosphorus, arsenic, and probably antimony. In fact, you have only 5 or 6 elements, and you will have to combine them judiciously so that it can support 1550 nanometer or a 1300 nanometer. And obviously, the material should be always a direct bandgap material. It should be a direct bandgap. So that is another, there is another design constraint. So you should be using a direct bandgap material. And also, this is also important, this lattice constant. So why is the lattice constant important? The lattice constant is important because these devices will have to sit on a substrate. So it has to, there should be a substrate which should be holding the device, and there should be a good matching between the device. So this is the device and this is the substrate. Just like when you construct your house, so you are constructing your house, but this house is actually built on a basement. You have a foundation, you have a basement on which you construct your house. So your house should be properly sitting on the basement. Otherwise, after a few years, you will be finding a lot of cracks and your house might collapse. So just like that, there should be proper lattice matching between the device and the substrate so that the device can properly work. So the lattice constant will also have to be adjusted properly. So there is in fact, there are materials called as ternary semiconductor material. For example, aluminum gallium arsenide and gallium arsenide. This is one material combination. The other material combination is indium gallium arsenide phosphide. This is the other material combination. So in fact, this material combination is the one which is going to support 1550 or 1300 nanometer, and therefore for this particular switch we'll focus on this material. So in fact, this material combination, this aluminum gallium arsenide and gallium arsenide, this is the material combination which is used in constructing the laser diodes. For example, if you have a laser pointer, so if you have a red laser pointer, so those red laser pointers are made out of this particular material. So either aluminum gallium arsenide or it could be indium gallium phosphide. This material is also used. Anyway, so ternary materials are used for constructing these lasers, whereas for optical communication, we generally prefer this particular material simply for the fact that it can support this 1550 or 1300 nanometer. So I'm not going to discuss about the direct band gap and indirect band gap semiconductors, but I would like to discuss something about what is called as quantum well structures. But before that, I would like to discuss about something about lattice matching. So I said that you have a substrate material, and then you have a device material. So substrate is the foundation on which you construct all the device. So you would ideally like to have a lattice match substrate. That means the lattice constant of the epitaxial layer and the lattice constant of the substrate crystal, they always should be the same. So this is which is mostly interested for us. But in some cases, you can always have some mismatch. So if you have a mismatch, there are a lot of drawbacks if you have a mismatch. So I'm not going to go into all those details. But anyway, so let us come back to our electro-absorptive ring resonator structure. So the operation is, the principle is, you have a device structure which has a semiconductor diode, something like this. You have a diode here, PIN diode. This has holes, this has electrons, and this is an intrinsic region. So whenever you apply an electric field, you have what is called as a quantum well here. So we'll see what a quantum well is. So we'll just focus on what a quantum well is. And whenever you apply an electric field, the absorption coefficient of this quantum well is the one which is going to change. So the quantum well, which is a semiconductor nanostructure, the absorption coefficient of this one would change. So I apply an electric field. To a quantum well structure, which is constituted by this ring, and this would actually cause the change in the absorption coefficient. So once you change the absorption coefficient of this ring, then this photon will not get coupled to this ring. If the photon does not get coupled to this ring, the photon will be appearing at the T port. This is how you switch it or you modulate it. Okay, so we'll see what a potential well is or what a quantum well is. A quantum well is just like the sandwich. So if you have eaten a bread sandwich, the quantum well is exactly like that. So in a sandwich, you have a center region, usually a vegetable or meat or whatever it is, and then you have two layers of bread which encapsulates this region. So likewise, in the case of quantum wells, you have in the center region is going to have a lower band gap material. The adjacent two layers are going to have a higher band gap material, which is made out of higher band gap material. So if you look at the cross-sectional image of a quantum well, it would look like this. So this center region, is the indium gallium arsenide phosphide. The other adjacent regions are indium phosphide. So I would call this as the well region. I would call this as the barrier region. So which means in my rectangular waveguide region, so this is a well, this is also a well, this is also a well. So this is well, and this one is also well. These are barriers, These are barriers, and on the top of this I'm going to have the p-dope region, and I'm going to have the n-dope region, so that this region, this entire region is called as the intrinsic region. This is the region which actually confines the light. So this is the core. This is the light core, which has a higher refractive index, and this is the cladding region. This is the cladding region. So now if you have a quantum well, you can actually draw the energy band diagram. So I'm not going to discuss about how you construct a quantum well. Unfortunately, we don't have enough time for that. Anyway, so consider that you have a quantum well like this, which is made out of this black region, which has a lower band gap, is made out of this particular material, whereas the higher band gap material is made out of indium phosphide. So if I draw the energy band diagram, you all know that for a semiconductor material, it's going to have a conduction band, the conduction band edge and the valence band edge. So for an indium phosphide, which has a larger band gap, if I'm going along this direction, if I'm drawing the energy band diagram along this direction, indium phosphide is going to have a wider band gap. So this thickness corresponds to this thickness. This thickness corresponds to this thickness. Now, once you complete indium phosphide, you are going to have the lower band gap material, which is constructed by using indium gallium arsenide phosphide. That has a lower band gap material. So the center region is the indium gallium arsenide phosphide, which has a lower band gap. So this is the conduction band of indium gallium phosphide, and this is the valence band of indium gallium phosphide. And then, so this thickness is actually this W. So this is W. This is W, and then this will be followed by a wider band gap material, so indium phosphide. So now I can just draw the energy band diagram for the quantum well structure. Now the fundamental difference between a quantum well structure and a bulk semiconductor structure. So this word quantum means I have what is called as the quantum confinement. I have what is called as confinement. Sorry for the spelling mistake. Okay, it's called as the quantum confinement. So if you have a bulk semiconductor material, is a three-dimensional material. If you have a bulk semiconductor material, if I draw the energy band diagram, which is conduction band and valence band, and if I have an electron in the conduction band, I have an electron in the conduction band and I have a hole in the valence band, this electron can have some energy. This electron can take any values of energy. That means the energy of this electron is going to be continuous. Yeah, so excuse me for the wrong spelling. So the electron in the conduction band can have any energy values for a bulk semiconductor material. A bulk semiconductor material is also called as a three-dimensional semiconductor material, where the electron is free to move in all the directions or in all the dimensions. But once you have a quantum well, if I put an electron inside this quantum well, so here I have an electron there. This electron, the motion of the electron is restricted along this direction, because if I have an electron here, if there is an electron there, this electron cannot go to the other side because indium phosphide has a higher potential. It cannot go to left hand side because again indium phosphide has a higher potential. That means the electron is confined to stay only inside this semiconductor material. That means indium gallium arsenide phosphide. In other words, the electrons are, I would say that the electrons are confined. So CONFINED. So electrons are confined. So the motion of the electron was restricted. So once you have an electron whose motion is restricted, it means that according to the Heisenberg's uncertainty principle, it means that if the electron motion is restricted, it should have some non-zero energy. So in this case, the least energy that is possible for the electron is 0. That is the smallest energy that is possible for the electron, and from 0 it can take any energy values what it can have. It can take any energy value. Whereas if you have an electron that is confined, it turns out that the electron will not be sitting here. Rather, the electron is going to sit here at an elevated position. The electron is going to sit at an elevated position. So the electron is going to sit here. This electron, this red region is what is called, so this particle is an electron. This is an electron, and this is what is called as a hole there. So that means, so this energy is called as the 0 point energy of the electron. It's called as the 0 point energy of the electron. In other words, I mean to say that if you have some electrons inside a quantum well, the electron can take only certain discrete values of energy. So it can take only discrete values of energy. So you can have electron states over there. So electron will be sitting there, the hole will be sitting there, and therefore now the band gap, which is defined as the fundamental definition of band gap is, it is the energy difference between the conduction band edge and the valence band edge. And therefore in a potential well or in a quantum well, the band gap in a quantum well is not just this energy difference, rather the band gap would be now is called as the effective band gap. The effective band gap is actually the energy separation between the places where, or the energy states where you can actually find an electron here and you can find a hole there. So every electron in the hole, you know that according to de Broglie, every electron will have an associated wave function. A hole will also have an associated wave function. Every particle has an associated wave function with that, and that is what is called as the de Broglie's principle. So therefore, the electron will have an associated wave function. The hole will also have an associated wave function. So that means now if a photon is allowed to pass through this material, if I have an incoming photon of energy h nu, a photon whose energy is h nu is smaller than this energy gap, which is smaller than this effective band gap energy of the quantum well, will not be absorbed by the photon. That means if I have a photon whose energy is slightly smaller than this energy gap, this photon will be allowed to pass through it. So that is some of the striking. So that is a striking feature of a potential of a quantum well. Now, I said that the electrons and holes inside a quantum well, they are confined. They are confined within this material. That means electrons and holes are restricted. The electrons and holes cannot move to left and right. It can move either vertically or it can move perpendicular to the screen. But along this direction, the motion of electrons and holes are restricted. Now, you know that electron is a negatively charged particle. So this electron is a negatively charged particle. The hole on the other side is supposed to be positively charged particle. And so you have two oppositely charged particles, but they are confined in the same region, which means the electrons and holes would try to attract each other. There would be some kind of Coulomb interaction between electrons and holes, and as a result, so there is some kind of Coulomb interaction, there is some kind of interaction between these electrons and holes, and as a result, rather than behaving as two independent particles, the electrons and holes would now behave as a single particle, and this single particle is what is called as an exciton. It's called as an exciton. So a single particle, which is actually a Coulomb interaction between an electron and the hole, which happens in the case of quantum well structures, is what is called as an exciton. So exciton is not really a particle, but in fact it is a fictitious particle which happens because of which is formed because of the interaction between an electron and the hole. So these excitons are formed when a photon whose energy is slightly smaller than the energy band gap of the quantum well is being absorbed by the quantum well. So excitons are formed. So you can form an exciton when photons of energy which is slightly less than the effective band gap of the quantum well. When photons of energy slightly less than the effective band gap of the quantum well is being absorbed by the quantum well, you can actually generate an exciton. So when you generate an exciton, what you are actually creating is you are creating an electron, you are creating a hole. But please remember, they are not two separate particles. They are now behaving as a single particle because of the Coulomb interaction, because of the opposite charge of electrons and holes. So whenever you form an exciton, whenever excitons are formed, you will see that if you look at the absorption spectrum of a semiconductor material, when you look at the absorption spectrum of the semiconductor material, you will see that you can find some sharp peaks. So if you look at the absorption spectrum, of a semiconductor quantum well, you will see that you will find some sharp peaks which are called as the excitonic peaks. Now what is going to happen? Now in our device, what we are going to exploit is, you apply an electric field and you want to change the absorption of the semiconductor material. That means you will have to reduce the band gap of the semiconductor material. So I'll give you some fundamental idea. So imagine that this is EC, this is EV, the band gap is EG, and you have an incoming photon whose energy h nu is less than Eg. You have an incoming photon whose energy is less than the band gap of the semiconductor material. So if you have a situation like that, if the energy is slightly less than the energy band gap, this photon will not be absorbed by the semiconductor material, because the band gap, the photon does not have enough energy to take an electron from the valence band and then put it into the conduction band, because the energy is less than band gap. So absorption can happen only if the incoming photon has an energy at least equal to Eg. It should be at least equal to or greater than Eg. Only in this condition the photon will be absorbed. So whenever I say that a photon is absorbed, what is really happening is the photon is being absorbed by an electron in the valence band. This electron goes to the conduction band. So you have an electron here and you have a hole there. You have an electron there and you have a hole there. And since they are Coulomb, there is a Coulomb attraction, I would say that you are creating an exciton. So when the photon energy is slightly smaller than the band gap, you cannot have photon absorption. But the photon absorption can happen only if the energy gap becomes, or when the energy of the photon becomes exactly equal to Eg or is slighter than Eg. Now let us see what happens in a quantum well when you apply an electric field. So this is the energy band diagram for a potential well, and you will note that the applied electric field is 0. There is no applied electric field to the quantum well structure. Now let us see what happens when I apply, and you will see that this is the bulk band gap, this is the effective band gap of the semiconductor material. That means, so what does this mean? Let's say that I have an incoming photon, so I would call this effective band gap as E1. So E1, this is the effective band gap. Now I have an incoming photon whose energy h nu is less than E1. The incoming photon energy is less than E1. Since the incoming photon energy is less than E1, this photon will not be able to create an exciton, will not be able to absorb, will not be able to take an electron from valence band and put it into the conduction band. And therefore, what would happen? This material would be transparent. In other words, this photon will simply propagate through that material without getting absorbed. The photon will not be absorbed by the material, and the material will be simply transparent to that photon. Now let us see what happens when you apply an electric field. So once I apply an electric field, so now I am applying an electric field in this direction. So here is positive, here is negative. I'm applying an electric field. Now because of an applied electric field, the band diagram, the energy band diagram of this potential well would bend like this. There is a band bending in the potential well, and because of this energy band bending, what happens is, now you have an external electric field. There is an external force which is acting on this electron and a hole, which means this electron, since there is an external force that is acting on this electron and a hole, this electron would try to escape from this well. This hole would try to escape from this well. And because of this external electric field, what would happen is this energy, the energy of this electron would come down, the energy of this hole would go up. So you would see that here is the positive side, this is the negative side. Since electrons are negatively charged and the holes are positively charged, you would see that the electron is now getting attracted to the positive side. That is why you would see that the peak of this wave function is moving towards the left hand side, moving towards this positive side, and the peak of this hole is actually trying to move to the other side. But please note that the electrons and holes cannot completely escape because of this barrier. But what is the other phenomena that has happened? The energy band gap has now decreased. Earlier the energy band gap was E1, but now this energy gap is now E2, and this E2 is slightly smaller than E1. So that means if I have now let us assume that I have a quantum well, I have there is no applied electric field, and the incoming photon energy is exactly given by E2, and E2 is obviously less than E1. And since E2 is less than E1, and since you have no applied electric field, the photon is being simply transmitted by the waveguide. But once you apply an electric field, the incoming photon, the energy of the incoming photon becomes exactly equal to the effective band gap of the semiconductor material. Because of which, what would happen? The incoming photon would be absorbed by the semiconductor material, would create an electron in the hole, and as a result, the semiconductor material would now absorb the photon. And therefore, in the output side, you will not find an the material would absorb the photon, and as a result, at the output side, which means in the drop port, you will not see any photon. So what would happen is, light absorption for photon energy is smaller than the band gap is really possible. So this effect is in quantum mechanical terms, this is called as photon assisted tunneling is also called as the quantum confined Stark effect. It's called as the quantum confined Stark effect. In fact, you can actually calculate how much is the amount of light that is being absorbed by knowing what is the width of the potential well, what is the width of this potential well, and what is the applied electric field. So you can actually calculate what is the absorption coefficient. You can actually calculate what is the absorption coefficient of a semiconductor material, and you can actually calculate, in fact, that absorption coefficient is actually a function of applied electric field and the quantum well parameters. So this is the absorption spectrum. This is the absorption spectrum of the quantum well semiconductor material when the electric field is not applied. But because you have applied electric field, you would now see that the band gap energy of the semiconductor has now decreased. If the band gap has decreased, it means that the absorption spectrum is now shifted, is red shifted. So it becomes smaller in energy, which means if I plot this in wavelength, it becomes longer in wavelengths. So if I'm trying to operate at a particular wavelength, so which means if my input signal to my ring resonator is operated at this wavelength, let's say lambda OPT, this is the operating wavelength, you will see that at this wavelength, when the field is zero, so please note, this is the absorption spectrum of the semiconductor material when the field is not zero. Sorry, when the field is zero. Field is zero. When the field is non-zero, the absorption spectrum is shifted towards the right. So I'm operating my device at this particular wavelength. So at this particular wavelength, my absorption coefficient is extremely small. That means the photon will almost appear at the output side. But once I apply the electric field, the absorption spectrum shifts towards the right, and as a result, at this particular wavelength, you have a large absorption now. You have a large absorption, something of the order of 10 raised to 4 per centimeter. 10 raised to 4 per centimeter means 10,000 per centimeter, which is a very large absorption coefficient, which means the material would almost absorb all the light. So once you apply an electric field, the material would absorb, the device would absorb all the light, and ultimately at output, you will not get any light. So this is the concept of electroabsorption. This is the concept of electroabsorption. So this is what is called as the quantum confined Stark effect, or in short, it's called as QCSC. So this is the fundamental operating principle of our electroabsorptive optical switch and modulator. So in fact, you can actually calculate all this. You can calculate what is the absorption spectrum. You can calculate what is the absorption spectrum for a optical switch. So basically what happens, you have the resonance signal at this point. You have the resonance signal here. If no fields are applied to the rings, your resonance signal would be appearing at this point. Now once I apply once I apply the electric field to the rings, there's an absorption that is happening inside the ring, because of which you would also have a change in the refractive index of the ring. So this change in absorption would cause a simultaneous change in the refractive index of the ring, and accordingly the resonance signal would now appear at the T port. So here the light will not appear here, the light would now appear at this point. So the light would appear there. So I said that there is whenever you apply an electric field, so I apply an electric field. So let me denote the applied electric field as F. I apply an electric field, there's a change in the absorption of the rings. There's a change in alpha of the ring, this delta alpha. Now, anytime you have a change in the absorption of a material, this is something fundamental to all the materials, all semiconductor materials or all dielectric materials, doesn't matter. So whenever you change the absorption of a material, you are supposed to have a simultaneous change in the refractive index as well. So I apply an electric field, I have a change in the absorption of the material, this would lead to a simultaneous change in the refractive index of the material as well. So I would call that change in delta. I would call the change in the refractive index as delta n. So this relationship, there is always a change in the. There is always a relation which gives the change in the relation of, which relates the change in the refractive index and the change in the absorption coefficient, which is called as the Kramers-Kronig relationship. So you can use this Kramers-Kronig relationship, and accordingly you can calculate what is the change in the refractive index for a given change in the absorption coefficient for a given material. So in fact, this delta n or this delta alpha is actually decided by the quantum well parameters. The quantum well parameters. Quantum well parameters are nothing but the material composition, and also the width of the potential well or the width of quantum well. So it's decided by the quantum well parameters, and it's also decided by the applied electric field. So you can adjust these three parameters, and accordingly you can actually decide what should be the contrast ratio. So what should be the contrast ratio between the on and off states. So usually you would always prefer to have a contrast ratio of something greater than 10 dB. That means if you have 100 photons, at the transmission port, you will be having only one photon at the drop port. So you have a ratio of something like 1:100, a rough estimate. So this is how. So you can actually quantum mechanics, you can calculate all these things. Now I said that you can switch the signal. So I'm putting resonance signal here. I'm putting lambda naught here. This lambda naught will appear either at drop port or it can appear at transmission port. So what are the parameters? How do I do that? I apply an electric field. So I can apply an electric field. So by applying electric field, I can change delta alpha, which is called as the electroabsorption. I call it as electroabsorption. Now, in some case, I can also so by electroabsorption I can make the lambda from here, instead of appearing at drop port, I can make it appear at transmission port through electroabsorption. Now I can also directly change the delta n of the rings. Rather than changing delta n through delta alpha, I can directly change delta n of the rings. Thereby I can make the light to appear at the transmission port. So that is possible by what is called as carrier injection. In the case of carrier injection, again I have a PIN diode structure. So I have here, I'm going to have holes, I'm going to have electrons, and here in the center region I have the waveguide, which is the core. Now this core is going to have a refractive index which is given by N core. Let me call it as N. Now what I do in the case of carrier injection is I apply a forward bias. So I connect a battery like this. If I connect a battery, what would happen? The holes from the P side would get injected to the intrinsic side. Similarly, the electrons on the N side would get injected to the I side. So I am going to have electron and hole injection. Because of this increased carrier density, the refractive index of the core would now become N core minus delta N. There is a decrease in the refractive index. So because of the injected carriers, the refractive index decreases, because of which you have a change in delta alpha. So N core, so when the field is 0, when voltage is 0, the refractive index is N core. When the voltage is V, the refractive index is N core minus delta N. So there is a change in the refractive index, because of which the light, the refractive index is changed. So the change in the refractive index would be decided by the number of carriers what will be injected. So thereby you can actually decide how much is the change in the refractive index change, what is the change in the refractive index. Accordingly, you can decide what will be the light that will be appearing at the transmission port or the drop port. So one means of changing the refractive index is by what is called as carrier injection, for which you apply a forward bias. You can also have a case where you have carrier depletion. Carrier depletion means you remove the carriers. So in simple words, you remove the carriers. Now, how do you remove the carriers? All you have to do is you apply a reverse bias. So reverse bias means I connect the negative of the battery here. I connect the positive of the battery to the N side. So this is a reverse bias. So once you apply a reverse bias, what does this do? This is the negative terminal of the battery. This is the positive terminal of the battery. So this negative terminal would attract all the holes. Similarly, the positive terminal will attract. So all the holes would be moving in this direction. The electrons would be moving in that direction, which means once I apply a reverse bias, the holes would move to the other side, the electrons would move to the other side, and accordingly, the refractive index of the core would now become N core plus delta N. So there's an increase in the carrier. There's an increase in the refractive index of the ring, and as a result, you can again make the light to switch either to the transmission port or to the drop port. So in this case, the refractive index change is actually decided by the number of carriers that are depleted, or in other words, that are removed. Okay, so these are some of the ways by which you can change the refractive index of the you can change the refractive index of the intrinsic region, and accordingly you can you can look at this figure. So you can have a you can apply a forward bias. I inject the carriers. The refractive index becomes N minus delta N, so that now you achieve this non-resonant condition. So in fact, you can calculate. You can quantum mechanically calculate what is the number of electrons and holes that can be injected. You can solve what is called as the drift diffusion equation. So all these are mathematical equations. There is no point in explaining all this. You can refer any textbook, standard semiconductor textbooks. You can solve this drift diffusion equation, and you can effectively calculate what is the change in the carrier density. So this carrier density is nothing but, in fact, this carrier density is nothing but the number of electrons and the number of holes. So this would ultimately determine what is the change in delta N. All right. So I think I have just explained to you how you can achieve the change in the carrier densities, how you can change the refractive index. So as a summary, you can have delta, you can apply an electric field, you can change the absorption of the rings. You can apply an electric field, you can change the refractive index of the rings. You can either increase the refractive index or you can decrease the refractive index by carrier injection or carrier depletion. So all these three mechanisms can be used for switching and modulating the light. Okay, so with that, I would like to stop here. So thank you all for your patient listening. So if you have any questions, you can ask them. Thank you.
Thank you so much, sir. Now let's move on to the questionnaire section. If you have any doubts, you can directly interact with the resource person. or you can note them in the chat box. So there are some doubts in the chat box. I will ask you one by one.
Yeah, okay, sure.
The first question is by Dr. Jisha PK. Which are the techniques to analyze material composition for the electroabsorptive ring resonators?
Okay, so in fact, when you're modeling this structure, when you theoretically design it, it's not a big deal because you can choose any condition, any material composition what you want. But one condition is that whatever material composition you are choosing, that should enable lattice matching. So that should enable what is called as lattice matching. You should have lattice matching. Lattice matching means the lattice constant of all these materials should be same as the lattice constant of the substrate. I think the question of Dr. Sajana is to find out how can you experimentally determine this material composition, right? Is that what your question is? How do you experimentally find the material composition?
The participant can directly interact with the speaker.
So if your question is how can you experimentally determine, then there are certain techniques called as X-ray diffraction technique. It's called as, it's not related, in fact those are certain material characterization techniques. It's called as XRD, X-ray diffraction. So in short, it's called as X-ray diffraction, by which you can really decide what is the material composition of the quantum well structures. I hope I have answered your question.
Okay, I hope the doubt is clear to Dr. Jisha. The next question is by Mukesh Kumar. Why is semiconductor laser always preferred in optical fiber communication?
Okay, so the question is why is why is semiconductor lasers preferred in optical communication? So let me see whether I have a slide for that. Okay, the advantage of semiconductor laser diode. So here is the keyword. So the question is, why is semiconductor laser? Why is semiconductor laser important for optical communication system? So what are the two important wavelengths are 1550 nanometer and 1300 nanometer. Now fortunately, it so happens that by adjusting the material composition of the semiconductor material, you can clearly decide what is the emission wavelength of the semiconductor laser. So there are two wavelengths, there are two precise wavelengths what you want. One is 1550, one is 1300 nanometer. So you can precisely adjust the material composition of the semiconductor laser, and you can precisely make a laser diode which emits either at 1550 nanometer or 1300 nanometer. Now this is possible because, so maybe I should take you to this slide. I'm sorry, I'll have to switch through multiple slides. Yeah, I think it comes from the fact that semiconductor lasers, they always use what is called as a quantum well. A quantum well is a lower bandgap material which is sandwiched between two wider bandgap materials. So if you are talking about fiber optic communication, the well is made out of indium Y, gallium 1 minus Y, arsenic 1 minus X, phosphorus X. So the band gap of the semiconductor material, the energy band gap of this particular material, the energy band gap is actually given by the separation between these two levels. This is the conduction band edge, this is the valence band edge. So the material band gap of a quantum well structure is decided by two things. One is, it is decided by the material composition. Material composition. This is one factor. The second factor is the band gap is also decided by the width of the potential well. This width, the width of this potential well will also decide the material band gap. So that means by adjusting either D or this material composition, you can precisely make a laser. You can make a laser diode which precisely emits at 1550 nanometer. Now, if you want a laser diode to emit at another wavelength, 1551 nanometer, so or let's say 1550.1 nanometer, even that is possible by all you have to do is adjust D or adjust the material composition X or Y. So in fact, that design flexibility is possible only with semiconductor lasers. With no other materials, you can have that kind of flexibility. Not with gas lasers, not with dye lasers or any other lasers. Only with semiconductor lasers, you have this extreme flexibility of precisely choosing the emission wavelength by adjusting the material composition and the thickness of the potential well. And that's why semiconductor lasers are being used. The other advantage is because semiconductor lasers are more efficient compared to gas laser. The efficiency of gas laser is extremely poor, and gas lasers are extremely bulky. Semiconductor lasers are compact, they require less energy, but more than that, this is the advantage. It's the flexibility in choosing the emission wavelength by adjusting the material parameter and the potential well width, which makes semiconductor lasers extremely attractive. I hope I have answered your question.
Yes, thank you, sir.
Yeah.
There is one more question by the same participant. Whether laser pulsed or continuous laser is preferred in optical fiber communication?
Yeah, okay. So if you can recollect direct modulation and external modulation, you can I think that would help you to answer this question. So in the case of fiber optic communication system, if you are using a semiconductor laser to minimize chirping, so to minimize, let me go to that slide. Yeah, if you look at this slide, to minimize chirping, you would always make the laser always on. That means you're going to use a continuous wave laser. You're going to use a continuous wave laser, but you put a modulator outside which will make this continuous wave laser to be a pulsed one. So once you have this bias plus data, the output would be 1 or 0. That means this is pulsed. But the laser is always turned on, which means it's a continuous wave laser. Yeah, any further questions?
Is clear for Mukesh Kumar. The next question is by Aswath. Whether the frequency of operation depends on choosing modulation schemes in radio over fiber.
I'm not very clear of this, so I think that I'm not very sure of this. I don't know. I'm not able to understand this question. So what you can do is you just send. So please send your questions to. So if you want a detailed discussion, so please send this question to my email address, or if you don't mind, probably at your free time, you can call me at this number 2385552. So this is my mobile number. So you can either WhatsApp me or you can just call me, and probably I can explain this question. Right now, I'm not able to understand your question.
Thank you so much, sir, for
So
your
please do that.
concern. Next question is by Dr. Amuda K. Sorry, it was a suggestion. Okay. The next question is by Nilaska Ghosh. Can both resonant and non-resonant ring structure used for sensing purpose?
If you want to maximize the sensitivity, it is always better to work with resonant signals. Non-resonant, unfortunately, will not be that helpful in that aspect. So it is always better to work with resonant signals. Because it is for the resonant signal that the device has the largest sensitivity. So you make the smallest change to the resonant signal, the device would significantly respond. So therefore, it's always better to work with resonant signals. Yeah, okay. Can you move on to the next question?
As I think the doubt is clear, the next question is by Ashwini. Due to the broad bandwidth of dye lasers and semiconductor tunable lasers, they are more preferred in locking the phases of a laser when compared to gas lasers. What is the reason for the broad spectral bandwidth of dye lasers, and why gas lasers have low spectral bandwidth?
Yeah, okay. May I know, this question is from a student or from a faculty?
It is from a student.
Okay, so okay, fine. Now, in the case of, okay, so so the question is more of fundamental type. So the question is dye lasers. Now you can classify lasers based on three types, based on the gain medium what you use. So a laser is having a gain medium. So it's having a gain medium. The gain medium could be solid, then you call it as a solid state laser. The gain medium could be, I think there are some liquids, but let's forget about that for the time being. The gain medium in the other case could be a gas. Then you call it as a gas laser. Now solid semiconductor is a solid, and therefore you call it as a solid state semiconductor laser. Dyes could also come under the solid. Now, if you look at the spectral purity of, if you compare the spectral purity of a solid state laser and a gas laser, it turns out that gas lasers are more pure. Now, spectral purity means if I plot lambda, the output emission wavelength from the laser as a function of output power. So P naught as a function of lambda is what is called as the spectral purity plot of a laser diode, or sorry, spectral purity plot for a laser. Now laser, you all know that it's a monochromatic source. Laser is supposed to be a monochromatic. It's not exactly monochromatic. It's supposed to be monochromatic. Now monochromatic means it should have, for a monochromatic, it should be having only lambda naught. There should be only one lambda naught. So only one lambda naught means the emission usually happens from an excited state. It usually happens from an excited state to a ground state. It usually happens from an excited state to a ground state. So if you want only lambda naught to be present, you should be having only one excited state. That means all the electron, the population inversion should be happening between, all the population inversion should be happening in this excited state, which is only one excited state and only one ground state. If that is the case, that is the ideal case. If that happens, then all this de-excitation would result in photons, which will result in lambda naught. But what happens is, in a solid, you know that there are large number of atoms.
Now, if you look at the electronic configuration of those atoms, they are going to have, all the atoms are going to have a vibrational energy. I mean, there are vibrational states, there are also rotational states, which means these excited state, this is not a single level, rather you're going to have multiple levels over there. It's not just one level. Similarly, the ground state is not just ground state, rather it's going to be ground states, and these are going to be excited states. So which means that in the case of solid, because of larger atomic interaction, you're going to have de-excitation that happens in and around a single ground excited state and a single ground state, which means if you look at the output emission spectrum of a solid state laser, you are going to have something like this, something very broad, but the majority of them is going to be at lambda naught. Whereas in the case of gas laser, the atomic interaction is extremely weak. The atomic interaction is extremely small in the gain medium, and therefore you are not going to have too many excited states. You are going to have something called as a discrete state. So in the case of gas laser, the de-excitation happens between discrete states because the atomic interaction is very weak, and therefore if you plot the spectral purity, if you plot the spectral emissions, if you plot the spectral emission of a gas laser, it's going to be less. It's going to be less, the bandwidth is going to be less. That means the de-excitations happens between, rather than excited states and ground states, it's going to be excited state and ground state. So this is the fundamental reason. Yeah, any further questions?
Thank you, sir. Does anyone has any doubts?
Yes, sir, I have one doubt. Hello, sir. Can you hear me?
Yeah, go on.
Hello?
Yeah, sure. You can
Hello, sir.
continue.
Can you hear me?
Yeah, I can hear you. Go on.
Yes, sir. Can you explain? Yeah, can you explain how the stimulation emission is taking place in the laser action time? I have always this doubt is there when I was teaching classes. Stimulation emission process, sir.
Okay, stimulated emission. Okay, then I will have to go to. So do you? So are we all? So I think our next session is going to start at 2:15. So
Okay.
if you don't mind, can we have this? I can definitely clear your doubt, but can we do this outside the session?
Yes, sir. Okay, sir. Definitely, sir.
Yeah, you can. I have dropped my email address as well as my mobile number, so we can have a one-to-one discussion.
Okay, sir. Thank you.
Yeah. So
If the
any further
participants
questions?
has any more doubts, you can directly mail or chat with the resource person. I think it's time to wind up the session. I take this opportunity to thank Dr. Sooraj Ravindran. Thank you, sir, for an excellent presentation. We are grateful for the time and effort you took to share your knowledge and experiences in the area of optical modulators and switches. Your ability to present the subject in such an interesting manner is really appreciable. We truly appreciate your willing to give your time and talents to enrich the knowledge of upcoming young minds. I would like to thank you on behalf of all the members present here. I hope you all enjoyed his presentation.
Yeah, thank you so much. Yeah, thank you for having me, and then thank you for the wonderful questions and for your patience. So, so if you have anything further, we can always discuss after this session. Yeah, thank you so much. Yeah, thank you.
Thank you, sir. The next session will be at 2:15, and I hope all of you will join at sharp time. And this session brings us to an end. Thank you all.